And all right. Well, it's open source, which is good because all this conference is revolving around open source technologies as well. And the reason open source is becoming so hot in the market as well is because people are moving away from proprietary protocols and proprietary vendors, because it's a very tightly vendor locked in environment, and open source gives us a vast majority, a big community which enables people for big opportunities of research and open research. So that's basically ONOS. It's a SDN controller, which is software defined. The second main part is software. What does software defined means? This is the only controller platform currently in the industry, which provides our transition from legacy networks to software defined networks. The transition, the migration is a huge challenge in any industry. If you're moving from your current environment to another environment, just even similar migrations are obtained, let alone a complete transition to new technologies or greenfield technologies. And on top of that, being software defined and able to hold and control all your software network elements, it provides service providers a real SDN and network function virtualization solutions. So that is the gist of the ONOS, what ONOS actually is. And if that is not reason enough why we need to focus on ONOS, we can look at its feature set. It's a very rich and thorough feature set that ONOS brings to the table. The top two features are a very core and fundamental requirement. It's high availability and its scalability. What does that mean? That we can have ONOS as a clustered deployment in any industry, in any aspect of the, whether it is educational, banking, in corporate, or any aspect of the industry, any sphere. Nobody wants a single point of failure. We always focus for a clustered, decentralized deployment so that we are not, we don't find ourselves at any stage uh, handicapped or prone to single point of failures. So ONOS has a built-in functionality to be installed as a cluster. It is very simple to install it in a clustered environment, and that brings us, it provides high availability. We'll look into a little bit more detail in future slides, but we have multiple instances of ONOS running. So even if one instance fails, the functions can seamlessly be migrated to the next without facing any kind of outage window. Scalability comes along with it, because if we have our workload, if we want to expand or we want a remote access somewhere else, all we have to do is spin up another ONOS instance and add it to the cluster. So scaling up ONOS is very simple. Then comes the flexibility. ONOS, being open source and being constantly being upgraded, has a wide research platform for improvement. So it has been performing and providing an excellent performance up till now in terms of its flexible architecture. What flexibility, how can we gauge flexibility? I mean, what I mean by flexible, being flexible here is that ONOS has a vast support for third-party integrations. It has both northbound and southbound APIs with which we can control the underlying control plane as well. In addition to it being integrated with the top application layer and controlling the application intents. So there is no problem in integrating our ONOS with, infusing ONOS into our architecture and fearing that what might happen, whether it will be compatible or not. So we use REST, there are REST APIs available, everything is open source, it's very open and for support and for integration. Simple and powerful abstractions. By simplicity, I mean, you will see how easy it is to have an ONOS deployed in your environment, and powerful in the sense that it gives you all the command sets or the features that you are looking for in any software defined controller. And on top of that, as was introduced at the start of this session as well, it has the support for optical emulations as well. So you can control optical topologies through ONOS as well. So it's a very simple and powerful abstraction. I hope all the audience, you all know what we are talking about here in terms of abstractions, because it's a software defined layer. So we have abstracted the control from the physical layer, and we have disaggregated the control and data planes. So we are talking about an abstracted control plane. So that is the point it has here. The rest of the points, well, we've already discussed that it is an open source, so it is not bound to any proprietary protocol or vendor behavior. And we've the next point we've also discussed about it's not bound APIs. The last point is also very important. I know if there are some techies in the audience, we all love a command line interface. I myself am very more comfortable using a CLI, but for many people out there, a graphical interface is equally as important. And for using ONOS, this thing especially comes handy, because we'll look at the ONOS interface in a little while as well. It has a complete, excuse me, graphical user interface with very significant information and a very detailed and thorough control interface for interacting with ONOS, using it, gathering information, and an overview of the graphical and the topologies that we emulate using Mininet or Mininet optical. As we were talking about at the start, that single point of failure is not a very comfortable situation that anybody wants to be in. So I'll just have it demonstrated how ONOS resolves this point of single point of failure. It's logically distributed, which means that all the ONOS instances can reside at different physical locations, and all we need is a network connectivity, a network mesh, a bridge between all the ONOS, so they can sync up. Logical means that it's not physically bound or anywhere. So you have virtual instances of ONOS running around the globe, and you can have them connected and synced up. All the distributed decentralized architecture of ONOS is symmetrical, which means that the exact same configuration is running on all the ONOS instances, which is also a requirement for it being highly available and logically distributed. Because if the configuration mismatches, we have a problem. We won't be, the controllers will come into conflict into each other. So ONOS ensures that all the ONOS instances are synced up and are symmetric. Being highly available, it is fault tolerant as well. I'll just show you in the next slide a very simple demonstration what happens. If one of the ONOS goes down, the primary role is simply shifted to the next available ONOS. It's location transparent. What location transparency means, that clients connecting to the ONOS are not bound by any parameter. I mean, we all, let's take the example of the Google search engine. We all use Google, and we are automatically connected to any of the servers, but those servers are region based. That's for our benefit, so we get the best latency and the best search results. So same is the case going on over here. If you have your distributed ONOS environment up and ready, there is no limitation that a particular client from anywhere is not able to connect to any particular ONOS controller. Obviously, there will be a set of rules and policies that we will implement just in case to provide the best performance. Obviously, it will be latency based and the purpose for the client that is connecting to ONOS. But why is this point valid for ONOS is that if the clients are bound by any parameter, what happens if that ONOS instance crashes? It has to shift to the other, right? So we cannot have this kind of limitation in our SDN controller that the clients are bound to connect via any parameter limitation. So that avoids the single point of failure as well. And the last point is again that is being highlighted multiple times, that being highly available and scalable, easily scalable, ONOS avoids being a single point of failure. So this is just a diagrammatical behavior, what might happen in a decentralized, highly available ONOS architecture. So we can assume that we have our 3 ONOS instances running in a cluster on the top, and there are some network elements or clients, any device that is being controlled by ONOS. So for this example, there's just 2 of them have been taken. For example, that in this particular set, our 2 nodes are connected to the leftmost ONOS server. So currently, for these 2 network elements, this ONOS is the primary role. This ONOS instance is playing as the primary server. What happens if this particular ONOS server fails? In a decentralized or a single point of failure environment, these 2 network elements will lose the control or lose the connectivity or go into a outage window, as we call in the corporate terminology. But with ONOS, what will happen is that the control will simply be shifted to the next available clustered ONOS instance, and the primary role will be shifted from the current ONOS instance to the next available instance. So this was a brief about how ONOS works, why ONOS is being such a recommended and favorable SDN controller in the market right now, what benefits it is bringing, and what feature set make it such a stable choice for disaggregated optical networks. Let's just take a 30-second breather and we'll begin with the installation. So to have the ONOS deployed in your own environment or for yourself, it is a pre-built ONOS virtual machine is available with the ONOS project, and the link is here as well. You can even search for it yourself. The OVA, you can simply download the OVA, deploy it in your virtual data center. Even if you don't have a data center, you can deploy it anywhere, in a workstation, VirtualBox, ESXi, Hyper-V, Microsoft, anywhere, it is compatible with all the operating systems, the common operating systems, Linux, Windows, Mac, and with all the leading virtualization technologies. So you can deploy this VM seamlessly on any. All you have to do is just download the OVA, deploy the virtual machine, fire it up. The username password will be present in the guide as well, which will come when you download the OVA. But it's a pretty generic username and password. It's ONOS and rocks. You can just log in, provide it an IP address, and there you go. That's it. That's literally all you have to do to have an ONOS, a pre-built ONOS environment in your configuration. So, but obviously it comes with a set of pre-built technologies and configuration protocols. So this available OVA can be used for a testing, a lab, or a demonstration point of view. If you want a full-fledged, fully controlled ONOS instance, so you can use the source project as well, using the source files that are available, just cloning the ONOS project, and the rest you can follow. There's a very simple guide to follow to install the ONOS, or you literally need just and 20 GB of free disk space to have your ONOS up and running. It does not have a very vast set of complex prerequisites. All the files are available in the repositories, and ONOS, you can yourself move forward step by step deployment of the ONOS as per your desired architecture, your desired cluster, the number of instances of ONOS, the IP addresses, different network subnets. So you can control all the if you want to deploy ONOS yourself. We looked at these commands in a live ONOS environment as well. But before we went there, I just wanted to display them as well. So we are not going into we are not looking at the CLI blindly. So just a feature set here. Mr. Mati has already walked you through a very comprehensive and elaborative Mininet session. So these commands will not be new for you. As you can see that this you are seeing here right now. Let me just walk through the commands that will be better. So the first command you see here is an activation command. What happens is that if you emulate the technology, your topology, sorry, not technology, you emulate the technology using the ONOS controller, you will have your topology present, but for by default, you won't be able to ping your instances. That is just our ONOS behavior. Similarly, like you have firewalls in your Windows, when you have your two operating systems up and running, you are unable to communicate unless you edit the firewall rules and policies. So similarly, you just have to activate your ONOS project. After that, you will be able, if you ping any of your two nodes in the topology, you will see that the connectivity is established and you are able to now ping them. These are a few, ONOS has a very lengthy manual of commands, but I've extracted a few which are very beneficial and which you go for in right away. So when you deploy, when you emulate a topology in ONOS, you want to see the information related to your topology. So here I think you have your devices, you have your flows, you have your links, you have your intents. All of those things are present in your topology. So if you want to see details regarding them, you can. If you now note that here previously we were at the Mininet console when we were pinging our two instances, but now we are at the ONOS console. So if you have your topology running, if you just type the devices, it will list all of the devices that are present in your topology along with their information, that whether they are using Open vSwitch or they're using some other switch, how long ago were they connected, are they currently standby or master nodes, and those kinds of all the parameters you see here. Similarly, if you want to see what is the state of the links that are connecting all the devices together, you can type in the links command and it will show you the state of all the links. In our example, all the states are active. So if there's an issue, you find some, like for troubleshooting, you're facing a cutout or you're facing an outage, you can simply come here, watch all your links and find out which link is deactive. All right, or it's a suspended state or it's not active. So you'll immediately come to know that which of the links is problematic and you can go and see there. As I said, it has both CLI and a graphical interface. So obviously you can perform the same activities on a web browser as well. So this is if you are more familiar with the command line interface. Here are the hosts which it resides on. So if you want to see what is the actual configuration of the underlying host, so you can simply type in the host command. It will give you the location as well, along with its IP address and MAC addresses, the IDs of them, and VLANs as well if there are any present. So you can come to know that on which VLAN or different kind of networks are your hosts residing in. Shutting down ONOS is very simple. There's another alternative command for ONOS as well. The O and K letters, OK. An OK command builds the ONOS controller, and a KO command will destroy your ONOS controller. So you can use that as well. But if you want to just keep your ONOS deployment intact and you just want to terminate the services, you can do the shutdown command as well. And the ONOS instance on which you shut down the command, it will only shut down that particular instance. So as you can see, the instance that this command was run was 172.17.02. So only the connection to this remote host has been closed. All the others are intact and running. So Here is the interface. I'll just show you this interface in a live browser as well. It will be better. But just before going there, um, here is the interface. You can see, basically you can see two interfaces because these are just screenshots. I had two different type of topologies ready. The above one is a simple tree topology. The lower one is a torus complex topology. So the things to notice here are what you get in a ONOS GUI server. First of all, you can see that there is an overview plane. You can, hold on, if I can get a pointer. Yes. So this is the ONOS summary pane. Here you can, in a very first glance, see that how many devices are present in your topology, how many links are there. Is it a completely virtualized logical topology, or are there any hosts connected to this as well? And what if there are any intents or flows present? So this box here right away gives you uh, overview, a summary of your topology. And on top, you can also see that on which ONOS version you're running. So you know if there are any updates available, you need to update that as well. The second you get is the instances plane. The instance plane refers to the ONOS controller itself. It's this box right here. In our lab, we currently have a single ONOS version running. So it's just one of them here. If you have a cluster deployment, there will be multiple boxes over here in different colors. This is blue or maybe yellow or red or anything. So you'll have the information directly uh, available about all. So if it's basically a single window management operations, you have all your uh, hosts visible through a single GUI. You don't have to log into each individual ONOS instance. So you log into ONOS, and since it's a clustered environment, you will see the details of all your instances in a single pane. The last two panes are not visible over here. It's a detail pane because you see the intents are zero right now. What are intents? Basically, intents, I hope you will be aware. If not, it's like a set of protocols that you write for. If it's an application intents, you have a set of rules or set of protocols. So currently, nothing is configured, so you don't have the detail pane. If you have all the environment properly configured and running, you will have a detail pane here as well on the left side. It will show you how many intents you have, what protocols, what flows you're using, and if there's any information related to that. The toolbar pane is also missing here. The toolbar pane basically it's just a view. You can shift your view. This is currently you're viewing the topology view. If you want to view your intents, you can simply click there. If you want to view your flows, you can simply click there. So it's just a navigation toolbar kind of pane that is available in the ONOS GUI. Moving quickly, let me just check on time. All right. So the researchers of the research paper titled mentioned here, the demonstration of software-defined packet optical network emulation with Mininet Optical and ONOS, have basically privileged us to emulate optical network environments using ONOS as well. So a huge credit to these authors here. They're doing immense work in this field, and they've actually developed an extension for Mininet. We've already walked through a very detailed session about Mininet. So optical, the link LINC, link OE, optical extension of Mininet is the Mininet's optical functionality, which provides you the capability, or which equips Mininet to emulate optical devices as well. Because Mininet is basically an emulator of the physical layer, the networks and the IPs. So if you have a Mininet optical instance installed, we have two components, the link OE and the link OE generator. So I'm sorry about that. So we have two components. They make up the Mininet optical extension. So if you have that embedded in Mininet as well, the SDN can then emulate optical environments in that. So we have, I have a diagram here. This diagram is basically courtesy of these authors as well. So as you can see that what I can do is, if I can hold on, type, yeah, that's it. If I if you ignore the red circled components here for a while, ignore they are not in this architecture. We have our host and IP routers. So you can see that this is what Mininet offers you, right? It offers you the emulation of your underlying hosts and IPs and network and subnets and each and everything. What Mininet has provided us that in an architecture or in an deployment in a data center where optical equipments are also present. As you can see, we've got our modem, we've got our transceivers if you have a transponder or any other optical network. So Mininet Optical has equipped ONOS with this functionality that now in your topologies, you can predict or you can show a display and control the optical networks. So what you have to do is the drivers are present, the drivers should be present for your optical network, just in the same way that you have installed Mininet Optical with Mininet, you have to install the drivers of your particular, the optical drivers of your particular optical network, say a ROADM in this case. So if you have a ROADM, you can install the drivers for ROADM, and then SDN will be able to emulate it using Mininet Optical. So this is a huge step forward in the in this research, because this conference is also revolving around the optical disaggregated networks, and this is actually what we have achieved in our laboratory as well. That we have a Mininet Optical. We have ROADMs, we have Momentum 20 white box ROADMs, and we have an SDN controllers. So we are fully equipped to move on with the emulation of our optical environments. Just a sec here, we have a few minutes left. I will switch my screen to the real environments and I will show you. Let me just share the entire of my screen. It will be.
Aneeq, sorry to interrupt. I think you are trying to rush up with things to wind up your talks. So you can take your time. You have 5 to 10 minutes extra. I think Professor Luca will start at 12:10. I just received a text. Okay. So you can go.
Thank you so much.
You can take your time, and then we'll have a QA session about your talk. So you can go along with the QA section. You can go until 12:10. Okay. So please continue. Thank you.
All right. No worries, no worries. We are right on time. Actually, this is when I wanted to start my demonstration as well. Thank you so much. All right. I hope you can see the screen here. Oh, we've landed on our machine. Let me just hide these meeting controls. All right, here we go. So we've got our ONOS and Mininet deployed separately because I wanted to use ONOS as a remote controller to test the remote functionality advertised for ONOS. Both of these machines are Ubuntu. It doesn't matter. You can use Red Hat as well if you want, or any other Linux. So for just the matter, if I bring you to the top, you can see that I told that an OK command basically builds your ONOS controller. So after you have all your configuration and installation packages ready for ONOS, this is the final command that you give to build all your packages. So you can see here that it starts the configuration and that it has a, the first time you will build your ONOS, it will take about 20 to 30 minutes. And with each respective iteration, then it will take about 10 to 12 to 15 minutes. It depends on the performance of your underlying resources. So in order to save time, I've already executed this command, so we don't have to sit idly and wait for ONOS to build. As you can see that there's a lot of scripts that go on. These are all the packages that you put here. Anything that you have not configured correctly will give you an error in the script, and then you will have to go and resolve that error and come back and build the ONOS again. So it's a hefty long list of all your packages and repository which is required. So it just goes and it configures everything what you're actually looking for is this last line at the end. When the ONOS is all done and ready, you will see this status update, that the update status has been updated to ready. That means that our ONOS is now ready. So if you use here's the is the IP address. ONOS usually talks with Mininet on the port 6633, and the GUI of ONOS is communicating on port 8181. So if you want to connect to your ONOS interface, you can put in your host name if you have the DNS entries in place, or you can have your IP address and port. So it will take you to your, this is the basically graphical. We'll just go to the CLI as well in a while. I just want to show you the graphical interface first. So just type in your username password for your ONOS controller, and it will log into your ONOS instance. So here we go. This is similar to what we just saw. That is why I wanted to show you that this is not a stranger place when we actually come here. Here is the user you're logged in with. Here is our summary. Here is our instance information. And then in the drop down, we have a lot of options here. You want to see if you've connected your application details, the cluster nodes, the packet processes. If you want, this is the part where I was talking about the topology, the navigation toolbar panel. So basically it wasn't visible there. So here you want to see your topology, you want to see your devices, you want to see your links, posts, intents. So you can simply navigate any of your processes through here. Let's just go to our, this is our Mininet machine. So it's residing on a different host. So let me just take you to, if you want to connect, all right, just let me do one thing. Let's not disturb this first. And I'm just spinning up a new ONOS. Yeah, okay. So if you want to control your ONOS via the CLI, all you have to do is type in the ONOS command. So ONOS connects to its shell using ONOS command as well. And this is the, oh yes, this is, I would like to, for benefit of all, when you are deploying ONOS, do not name your virtual machine ONOS. All right, or even create a user called ONOS, because you can say that ONOS is a pre-taken keyword for this controller. So it will conflict with your functionality if you name it. It will give you bugs and errors that you won't realize that why you're facing those errors. So
Aneeq,
this is something, sir.
Aneeq, really sorry to interrupt again. The physical audience, the font is quite small for the physical audience. So if you
All right,
if you
all
can
right.
just
Yes. Yep.
slightly.
Thank you so much.
Thank you.
Thank you so much. I hope it's better now.
Yes, that's fine. Thank you.
Perfect. All right. So moving forward, ONOS, and then you type in your instance which you want to connect. So I just have a single instance is running here. If you want to connect to any other, you can just type in the IP here. So I want to connect to my local instance. So here you go. Now I am in the.
Can you hear me?
Yeah. Yes, I think Mr. Luca is here. We can hear you. Would you like to add something, or can I continue?
No, Aneeq, you can conclude in 5 minutes, no problem. I mean, Professor Luca will start after once you conclude in 5 minutes, no problem.
Just give me a few minutes. I'll wrap up soon. Thank you so much. All right, so now we've connected on our ONOS console. Let me just quickly deploy something here.
Hello, everyone. Can you hear me?
Yes, Professor Luca, we can hear you. Can you hear me?
I'll just take 2 more minutes, and that will be all. I'm just, yeah. you will be able to see it now.
Okay.
So basically what I'm doing is I'm connecting, using a remote controller.
I don't know if they can hear me because.
Yeah, they can hear you. Did you listen, but
No,
said you didn't hear.
no.
Oh, okay. Because I told them, wrap it up in 5 minutes and we'll be here and we will come.
I don't know.
Okay, then.
Hello, hello?
I
No.
could hear you.
Can you?
Yeah, I could hear you.
So do you think it is good that
Yeah, yeah.
I go and then, but no one is going to, I mean, I don't have feedback from the audience.
I think Mr. Luca is unable to.
Oh, okay. Now I
hear
can
us.
hear you. Fine.
All
So
right,
it's-
all right.
so-
Yeah, we've been able to hear you from the start. Thank you so much. Just give me 2 more minutes. I'm wrapping up here.
Okay, perfect. Thank you very much. I'm here.
Thank you. All right. I've just used my remotely installed ONOS installer to make a simple topology. So if you come here and see, here's a topology. I've just created a simple tree topology using 3 nodes. And you can see the information is populated at real time over here. And now I'm in the Mininet console. So if you just see, well, I'm not going to go into Mininet because Mr. Mati has already been walking through it. So just a brief demonstration. Now, if you want to destroy this topology, you can simply run C. But note here, what happens that even if you've destroyed the topology, ONOS still has it. So you have to come over here and you have to wipe out the technology from. I really love this ONOS interface, because it is unorthodox. Like I've never seen a command language that wipe out please. So I requested ONOS to wipe out, and now it has destroyed my topology. So that was a brief demonstration how you can actually use a remotely installed ONOS instance with your Mininet. That will be all from my side. The forum is open for any questions and feedback. Thank you.
Thank you so much, Aneeq, for this nice illustration and a walkthrough through ONOS and Mininet. Before we move on to Professor Luca for his invited talk, we can take a couple of quick questions if someone has. So in the chat, Aneeq, okay, so Dr. Fahim has posted the corrected URL.
Thank you so much. Yeah, apologies for that. I'll have that corrected.
Yeah, and Usman Azhar is asking which open source orchestration ONOS deployed. Do you have something to comment over that?
I'll have to get back on that because orchestrator is not currently here in our lab.
Yeah.
So
yeah, yeah. I mean, you haven't.
We don't have an. Yep.
Yeah. So Usman, Aneeq will get back to you on this. I have your email address, and I'll hand it over to Aneeq to get back to you. Okay. So if there is no other question, we can wrap this talk. Is that okay from the physical audience? Any question? Okay. Right. So Aneeq, once again, thank you very much for your talk. And
Pleasure.
yeah, thanks a lot. Thanks a lot. So Professor
Pleasure.
Luca,
Thank you.
You can hear us, right?
Yes, sure.
Okay, perfect. So let me first make you a co-host so that you can share your screen.
Yes.
And then let me just introduce you first so that everyone knows. So Professor Luca Poti is the head of research area with the Inter-University National Consortium of Telecommunication, famously known in Italy as CNIT, at the Photonic Networks and Technologies Lab. And he's also an external collaborator for the Scuola Superiore Sant'Anna Institute of Communication, Information and Perception Technologies, again famously known as the TCHIP Institute, CECIP at the School of Superiore Sant'Anna Pisa. And SSSA Pisa is the project partner, our project partner in this project. So he's also professor at Universitas Mercatorum. Sorry for the bad pronunciation. He has published 1 book, 6 book chapters, and more than 400 international journal papers, conference papers, and patents. He has served as a coordinator and a scientist within more than 45 industrial and institutional international projects. In 2011, his group in Pisa demonstrated together with Ericsson the first coherent system working at 448 gigabit per second on an installed commercial apparatus in a field trial hosting real traffic. So that was quite a famous experiment in the optical community. And then the same experiment was repeated in 2012 with an upgraded value of from 448 gigabit per second to 1 terabit per second super channel in the flexible grid optical environment. So thank you so much, Professor Luca, for joining us. And I hand it over to you to please take it away. It's all yours.
Okay. Thank you very much. Can you hear me? Yes.
Yes, we can hear you.
Okay, okay.
Just a quick confirmation from the virtual audience. You can hear Professor Luca as well, right?
Yes, we can hear.
Okay, great. Okay. First of all, thank you very much for your kind introduction. And at any time, of course, you can stop me for any question or or curiosity. I will show some activity about our research interests, especially in high capacity optical communication. So here I have some material that I even did present in some conferences and internally, and some training material. If you have any question at any time, please. I use this title because it is interesting. It was, back in 2-3 years ago, when we were talking about high capacity for 5G networks. And that was like a forecast, what will be the network for 5G. And I'm keeping the same, title, let me call it title, but it is not a title, the same topic, because actually 5G seems to drive even in the evolution of the world's 6G. It is driving even all the network segments, and from technical point of view, it's not only driving the social experience and technologies for industries and for the world environment, but even, of course, for the physical layer, where I'm mainly working on. So the idea was to have a society that was fully connected, with where every person. I took this from a perspective of Ericsson, that is a very well-known company working in telecommunications, especially in mobile communication, but they have even optical systems, and we have a strong collaboration with them here in Pisa. And the vision is to have a networked society where every person and every industry is empowered to reach their full potential. Let me use some pointer here. So, yes. Okay. So they, highlight this time frame, let me call, in terms of generation of technology. So mobile, the foundation of mobile telephony in 1G in 1980s. In 1990s, the mobile telephony was for everyone. I remember I was starting my university around here, and I had actually my first mobile phone. I bought it was like somehow expensive, but I had. And 2000, the 3G mobile broadband foundation, and then 4G in 2010. That was mobile enhanced. Now we are still in the transition between 4G and 5G. It was supposed to be in 2020. We have an embracing networked society, and some of our mobile phones, they are already they are ready and they are using 5G technologies. But there is still, there is something that is changing very quickly nowadays in order to, completely exploit the 5G potential, and even trying to understand how the behavior, our users and technologies will change in the for next future. That means in the next 5 to 10 years. So the idea was not limiting access to information and sharing of data anywhere and anytime for anyone and anything. And so this will, will be, it's almost now. Some highlights here for what concerns some application in order to understand the real feature that we are addressing and that are very important for communication and for the quality of the connection. And still taking the example of the wireless access, the 5G wireless access from Ericsson, but that is very straightforward, the connection with the transport layer and the network itself. So we have here some examples that are very interesting. For example, some broad experience anywhere and anytime, a crowded event, for example, where you want to, all of the people, they want to have a good connection because they want to share some multimedia content with their friends, for example, or mass market personalized media and gaming. Even this is very, attractive, and it is very important for the characteristics that you want to have. For example, high data rates, and even some very low latency if you want to have the feeling of having a gaming experience. But even more important is meter, sensor, and machine type communication. That is even in this case we need to have in certain application very low latency, in other application high flexibility, or other application you need to have very high capacity. So all these applications, they are driving towards the evolution, the progress of the technology. Remote controller machine, transport infrastructure and vehicles, so they have to interact with each other, human machine interaction, and even much more that we cannot even imagine. So a wide range of requirements and capabilities, a flexible, scalable, and future-proof solution. So here are some features: very high traffic capacity, high data rates everywhere, very low latency, massive number of devices, very low device cost, very low device energy consumption. And the device cost and device energy consumption is even much more, important now, because these were, we already put a lot of effort in high capacity and data rate and low latency, but and we now have to, try to reduce the device cost and the power consumption and the energy consumption, and of course reliability and availability, even for and machine type communication. I would add to this list that is somehow included in reliability, even security. That is very, very much important nowadays, because everyone now feels to be connected, but want to be sure in the connection and secure in that connection. So that is very, very important even at the transport layer, where you can add some security technologies. So just to highlight two different of machine type communication in order to understand the needs. So for example, here is in some probably some plan where you have sensor actuators and a network that need to be capillary. So you want to have remote locations, so you have ultra long range. You want to have low protocol overhead to reduce battery consumption. You need to have low cost, low energy, small data volumes, and massive numbers, and must be a scalable access, not connectivity, either many of few devices. You want to have a flexible access to this infrastructure. Capillary networks and short range radio even can be included. On the other hand, for example, you have a critical machine type communication in industrial application or traffic safety control or tactile internet or smart grid. So in this case, you want to have ultra reliable, very low latency and very high availability, because you don't want the interruption of your service. It is very critical. And let me add again some security issues here that are inside the high reliability, but it is not just reliability itself, but you want to have a secure connection. So at the end, what we see, what they see as Ericsson 5G is nothing more infrastructure that serves everyone and serves the cloud. So you need to have all the technologies here that can allow for that. And this is true even in the evolution of towards 6G. So 5G is there, is here, but it's not still completed in the transition. And then we want to go, we are already talking about, sorry, to 6G. I have here some other use cases I'm just going through in order to, I already mentioned about these. For example, broadband access in dense area. So here we have a traffic density, several terabit per second per square kilometer. Or here you have a broadband access in a crowd, in an event, for example. So in this case, you have a terabit per second by time bounded. So you don't want to use, to dedicate this infrastructure to that stadium, for example, but you want to share with other in order to save the cost. Or, for example, here you want to have in surgery or remote surgery or in factories, you want to have ultra low latency. It means less than 1 milliseconds end-to-end latency. And even this, that it is not always considered, it is high user mobility. For example, in the trains, high-speed trains, when you want to have, you want to reach speed up to 500 kilometers per hour, and you need to have, you want to have a good connection. I always had bad experience in the transportation, even in Italy with high-speed trains, where you always lost the connection, is not reliable enough. So we are mainly working in photonic, and so there are a number of points where photonic technologies play a role in 5G, and we have activity more or less in a lot of this in this group. So this was used again from Ericsson, because they are targeting mainly multi-antenna technologies, but even fixed access and 5G transport and in cloud infrastructure. And of course, we are with them in that, and even our research is mainly focused on the access, transport, and of course, if we can provide some outcome in the multi-antenna technologies and the cloud infrastructure, it is welcome to our partners. But it is our even research interest. If we jump into the 5G transport, that is more related to our activities. So here is the standard, let me call segmentation of the network, where we have the access part that can be either mobile or fixed, that is generally is related to a distance between 0 and 10 kilometers. So we are talking about short distance. Then we have aggregation and metro network, where we have a distance that you want to cover between 10 kilometers and 100 kilometers. Then here you have in the standard network, you have the edge router, and then you have the real transport, that is the regional and core network, where you have core router and an infrastructure that must cover a range between 100 and thousand or more of kilometers. And if you think about that, then you need to have different kind of technologies covering this infrastructure and providing the good connection and the needs that you want to, the feature that you want to have for that. If you go back, we see what was it is said today, but it is still quickly evolving. But it is like in the transport we have mainly dense WDM and OTN technology in a red network with a topology that is ring or mesh, and the capacity, the overall capacity is 100 gig up to 1 terabit per second. And this is, an overestimation of the today network. I can say 1 terabit to 10 terabit now in the regional and core network. And for what concerns the metro, we have Ethernet switches or even dense WDM again, and the topology can be ring, bus, tree, mesh, any kind of topology, and the capacity must be between 10 and 100 gig. Even in this case, probably we are, it is slightly larger because most of the traffic is going towards the access, and this is a very key point that we will discuss further in the following. And for what concerns the access, we have passive optic network, Ethernet or peer-to-peer, and the topology is generally is 3 and peer-to-peer, and the capacity between 1 and 10 gig. We already have some 10 gig interfaces even for the final user, and so we just have to scale a bit these numbers. So the point, if you look at the 5G, the technology must be any technology that can provide the capacity between 10 and 100 gig in this access segment, and topology any but mesh, because it will be not possible to use this kind of topology with such capacity in the access. And for what concerns the metro, we are having dense WDM, and the topology is still ring, but can be even mesh, and capacity between 100 and 1 terabit. And in the core, the topology is ring or mesh again. We have the same technology, dense WDM, OTN, and the capacity between 1 and 10 terabit per second. So we see that the critical bottleneck is around here, because if this access is 10 to 100 gigabit per second for the user, then what will be the capacity of the metro and regional core? And as I was telling you before, the density of the traffic is moving around. At the beginning, in the traditional network, we had the access with low capacity, then the metro with the high capacity, and the transport with large capacity. But nowadays, the most of the traffic is going very close to the access, and so we have to figure out how to rethink the network in order to allow for this evolution. And there are technical interesting key points here, and the possible evolution at the research and even development level. So some challenges that are for 5G transport and even 6G. So the capacity can reach 100 gigabit per second in the access. It means 1 terabit per second in the delegation one. So now it is feasible with 100 gig coherent dense WDM that is based on the dual polarization QPSK modulation format. It was expensive. Now I have to say it is not too much expensive. Now we still have 200 gig coherent dense WDM that is based on dual polarization but 16 QM, and we are growing faster and faster. We are already working on a solution for 400 gig on a single carrier and larger capacity. For direct detection, and this is feasible with the coherent transmission system. I will detail on that. For direct detection, we have 100 gig. We can use PAM4 or DMT. Now PAM4 is playing more with respect to DMT is much more diffuse, but there are limitations in that, because PAM4, even if it is a straightforward evolution of standard on-off keying signal system, it has some problem when you have a large capacity, when you have large frequencies, large baud rates, in that case, the electronics is not good enough. At the moment, we have a strong limitation, the noise limitation, and even OSNR limitation, because we have multi-level. And so the additional noise can come from amplifiers, for example, that they can provide, strong impairment. And of course, we have to deal with the chromatic dispersion of the optical fiber, because we are talking about dye detection, so we don't have a dispersion compensation unless we put a specific dispersion compensation element or fiber at the end or into the link. And 10 GB per second, that's again sometimes applicable in combined with statistical multiplexing, and this it is something that has even is having an evolution in the last few years. For work content connectivity, we are figuring to have more than 100 connected radio sites, and but much more important it is the latency for transport. It must be 10 to 100 microseconds, so less than 1 milliseconds. And all these kind of latency, we must understand that 5 microseconds per kilometers is only for the propagation into the fiber. It is the physical, the speed of the light into the fiber. So we have to think that we will have this intrinsic limitation in the latency. And then, of course, other performance like the jitter or the delay difference in the communication. So what are the research directions? So we have, as I mentioned, 200 gigabit per second on a single optical carrier is a product. Beyond 200 gigabit per second transmission on a single carrier is needed. We are working in collaboration with companies for 400 gigabit per second, and then we will have 1 terabit and probably 1.6 terabit per second. And one of the key points is to have more information in the same bandwidth, because bandwidth is limited, we will see in a while. And so we will need even a higher spectral efficiency. And for doing that, we can use complex, we are using complex modulation format, that is QPSK, DQPSK in dual polarization, 60 QM in dual polarization, but we can go even for 64 QM. Now we are using the constellation shaping, that is a statistical procedure to have some sort of shaping of the constellation in order not to have uniform probabilities for all the symbols in the constellation. And we can even have coherent detection with digital processing. We will see a little bit about that. But in the time, I think the feeling is that coherent detection, direct detection, even with digital processing, even coherent detection, but direct detection we can exploit. We can stress more in order to still have to use in the system, but they will gradually disappear even in the short range communication. And for what concerns the evolution, of course, single channel or WDM system, they have multiple carriers, and they must be compatible with current optical transport network. And this is a problem from what concerns the architecture, because as I mentioned, we will have an evolution of the architecture, because it's an evolution even of the capacity that is needed in the different places of the network. So let me go a little bit more in the technical details. So we are aware of what is the optical bandwidth of the fiber. These are typical, attenuation losses with respect to wavelength, and the standard transmission windows that is around 800 nanometers or 1.3 nanometers or 1.5, 1.6 nanometers. That was, these are L band. So what can be done in order to increase the capacity of our network? So we first, what we are doing is to extend this bandwidth. So we want to exploit more bandwidth of the optical fiber, and if you look at the curve, the this red straight curve here, then it is one of the latest fiber. So these absorption peaks, they disappear. So in principle, we can have 800 micrometer of whole spectrum available for the transmission. So the first thing that we want to have is to extend the use of we can do is to extend the use of the bandwidth, but we have a limitation. It is at the moment we do have some amplifiers that are needed in any, more or less in all the applications somewhere, and the amplifiers are a little bit still limited to C and N band. Now we have some amplifier in the S band. Then we have semiconductor optical amplifiers that can cover a larger or broader ranges, but they have limitation in terms of nonlinear behavior, in terms of noise. Or we can have Raman amplifiers, but all these, there is not a consolidated technique in order to have very broadband amplifiers. So that is a key point in the recent research activity. So this is standard WDM with ultra wideband approach. So we want to cover more than with respect to the C and the L band. We add S band, or we can close the gap with the second window and use the whole bandwidth. We have even another possibility to have space division multiplexing. We already have installed fiber bundles, and we have actually somewhere even installed. We have a site in Italy, in L'Aquila, of CNIT that we own, where we have multi-core fibers deployed into the field, into the city. Of course, that multi-core fibers is used for research purposes. But at the end, you can try to understand if this kind of space division multiplexing, you have a space diversity in the connection. You have 4, 7, 11, and a number of cores that you can exploit at the same time. So now we have still limitation, but it is attractive. But of course, we still need amplifiers for multi-core fibers. And there are a lot of already deployed standard single mode fiber in the field, so we want to use them. And so at this stage, unless the cost will decrease for the fiber, or we will have more amplifiers, multi-core amplifiers, we will not go in that direction tomorrow. Probably it will be interesting to see in 10 years what will happen. And we can even exploit multi-mode communication, because we have digital techniques in order to recover for modal dispersion in the fiber. So you can use different modes and make them propagate together into the fiber, and then you can still recover the information. Sorry. So for what concerns coherent receiver, just to give you some more analytical detail of what is the benefit and where the benefit comes from about the coherent transmission with respect to IMDD. In the coherent transmission, we have this is the standard coherent receiver, where we have the signal that is coming after propagation, and then we have a local oscillator. It is another laser with it is here with energy ELO, and so they can have in principle a different frequency, omega 0 and omega LO, and so they are coupled together with a beam combiner, and then they are detected using a standard photodetector that makes the square of the field that is entering. So we have these two fields, and the square will give us the power at the output, that is nothing more than the power of the signal plus the power of the local oscillators, but twice this contribution that is given by the product between the two power of the signal and local oscillator, and this consequential function, because we have the real part here. And you can see here that the frequency is nothing more than the beating between the two frequencies. So the sum and the difference depend, and in general, it is the difference of the two frequencies that goes into the bandwidth of the detector that has a limited bandwidth. So you just have one single signal that is in the difference of the two frequencies, and then you have the phase of the signal, the phase of the local oscillator. So if we relate this the power of the signal to the amplitude through this k constant factor that is can be the responsivity of the photodetector, for example, then we have PS related to the AS and PLO related to the ALO, so the amplitude of the local oscillator signal. So we have the first case when we have two cases actually that we use is the homodyne and the heterodyne. In the homodyne detection, the intermediate frequency is 0. That means that this omega 0 is equal to omega LO. So you have the same frequency of the local oscillator and the signal. And if you make calculation here, now the K is exactly the responsivity of the photodiode, and IT is the current it is flowing through the diode. And so you have exactly the same equation. If we assume to have the local oscillator power much higher with respect to the signal, that is, the signal is reaching the photodetector, so it is after transmission. So we supposed to have very low signal and a very high local oscillator because the laser is there at the receiver. So this contribution can be approximated with the power of the local oscillator. So in this case, if it is supposed even that the phase of the local oscillator is locked with respect to the signal phase, so these two contributions are equal, so the cosine function is 1. In the best condition, the photodetector current is given by 2R and then the square root of PS PLO. If we compare to the direct detection, so we have the power of the signal times R. So if we make the comparison of the average electrical power, then we have 4 PLO divided by the average optical power of a signal that can be even large, very large, even larger than 20 dB. So we have a very high gain that is given, of course, by the injected local oscillator power that is there, that is representing a gain at the end, like an amplifier. So we have a very large gain, and we can reach a very high sensitivity at this receiver. And we have the heterodyne detection, where the two frequencies are not equal. They have a difference. The difference is omega IF is not 0. And then we have still we can write the same term of the current, and we see that still we have the current that is proportional again to the same value, but multiplied by the cosine function that now it is not 1, even in case they are locked, because we have an intermediate frequency. And if we make the average of the cos square theta over theta, it is 1/2. So we can see that in the case of heterodyne detection, we have at least a 3 dB penalty with respect to homodyne. But in general, these can come with a simpler receiver. So sometimes we can use heterodyne and sometimes homodyne. Actually, what we do in practical system is to use homodyne, but with a local frequency that is not exactly the same, is nominally the same, and we call this system intradyne. But you can think to have a homodyne receiver because the frequency is almost there, and we can recover this small frequency difference through the DSP after the A to D conversion at the receiver side. We can even go, make something more if we use balance detection. So the same scheme with two balance detectors. The balance detectors are nothing more than two detectors where they are in principle they are identical, and so we have they generate two currents, I1 and I2, they are subtracted at the end in order to have the final I. So if we apply the same results as before to I1 and I2 to the two photodetectors, then we can have the IT is I1T minus I2T, and so in this case we have this twice R PS PLO, and we cancel out the PS and PLO that are constant term into the receiver side. So we just have the cosine component that is the in-phase component with respect to the local oscillator fields. But we can even make more. So we can have the phase diversity homodynamic receiver, and we have this device that is called 90-degree optical hybrid, and these accept as an input the signal and the local oscillator, and the output provides these four terms where E1 is nothing more than 1/2 the signal plus the local oscillator, and then we have E2 that the signal minus the local oscillator, and E3 in 4 is the same but with a variation, a rotation of 90 degrees. So we have E3 is ES plus JELO, and E4 is ES minus JELO. And we have again balance for detection here, and in this case the output current here IT represent the cosine, the IQ represent the sine. So in this case we have we record for the I and Q component of the incoming signal. So if we have a standard complex signal that is reaching the receiver, we will recover exactly the in-phase and quadrature component here. And this is very strong because when you have in-phase and quadrature component here, then you can apply in the digital domain any kind of transformation. So you can recover for the chromatic dispersion, you can recover for polarization mode dispersion, you can try to handle for or process for accounting a little bit of nonlinearity into the fiber. So that is very strong, and that is the reason why actually there was this migration towards the coherent systems in the last 10 years because of the limitation induced by chromatic dispersion first. Then by using a coherent detection, you have a linear relationship with respect to the incoming signal, and then you can recover, you can process the linear system and trying to make an equalizer or to, invert the transfer function of the channel, and so to have to cancel out degradation due to at least linear phenomena. Then you can even have include the two polarization. So you have the same system where you have two polarization, and so you have a signal on polarization X and signal on polarization Y with a certain splitting ratio. This now is alpha. This alpha is between 0 and 1. It is 0.5 if you have exactly 50% polarization on one side signal and 50% of the polarization on the other signal. Sorry, 50% of the signal on one polarization and 50% of the other signal on the other polarization. And then you can even split the local oscillation by 2 and the two polarization, and still have two optical hybrid 90-degree optical hybrid couplers, and then you can have the 8 output signal that can provide the IQ and IQ for the two polarization. So in case you have, for example, a polarization multiplexed complex transmission system at the output here at the receiver side, you can recover for the two polarization, and the two polarization, they carry the two complex signal with I and Q signal recovered as a current, then can be converted into digital signal to an analog to digital converter. And this is what is done exactly in the reality. And here, okay, you have exactly the calculation for the photodetector currents, and then the currents that you have in the X polarization and Y polarization, as I mentioned, I and Q and I and Q, the component, both component in phase and quietly. So what are the advantages with respect to the IMDD? Now we know. First, the sensitivity can be very high, is very high. So the short noise limited receiver sensitivity can be achieved with a sufficient local oscillator power. So you put all the power in the local oscillator, and that is a gain. So you can have very, very, very low signal coming at the receiver. And it is very good. So it is almost, you can reach almost the short noise sensitivity. Then you have a frequency resolution at the intermediate frequency. You can always move a little bit your local oscillator, and you can select in electrical level the signal that you want to receive. Like in standard radio receiver, you can use even a PLL and a digital PLL in order to lock your signal and to just address the signal, the portion of your signal that you want. And you can even apply this to a standard Wave division multiplexer system. Then, as we mentioned, the ability of phase detection can improve the receiver sensitivity compared to the IMDD system. This is due to the fact that the distance between symbols that are generally expressed, can be expressed as a phasors on the complex plane, is extended by the use of phase information. This is nothing more than what I was telling before. If you have a phase information, you can, and you have your signal in the linear part of your signal, then you can apply all the transformation, all the linear transformation that you want in order to recover for the degradation of your channel, that can, all the linear contribution of the degradation of your channel. For multi-wave modulation format such as QPSK, but 16 km or 64 km, etc., can be used, and actually they are used in optical communication by using phase modulation. Okay, having said that, let me, I have to do this. It's just for fun, but I was using this picture. So we need a crystal ball for guessing what will be not only the driver but the solution for 5G. I will go fast in this because it was really for fun. That was this kind of forecast that was given by Christian Davis in 2010. So the forecast was that by 2020 it was hands-free texting, and actually we have. And even Sweden is an oil-free country. I don't think so still, but stem cell news, etc. So we will expect floating hotels in the sky by 2042. And Mars population, it was, really funny. And this is interesting. Even in 2095, most of today's languages aren't in use. Really, it's just to, really for fun. And by 2200, poverty, hunger, and disease are eradicated worldwide. This is the wish more than the forecast. But going more in the serious view, I got, I went to this picture that was given by Carlotta Perez, and I found this very, very much interesting, even to be applied to telecommunication. So she was looking at the grid surges in the history, and they, she said that they have a specific phases, one installation and the other one is the deployment. For example, here I have listed here the industrial revolution, steam, railway, steel, electricity, and the heavy engineering, oil, automobile, and mass production. And the last, it is information and telecommunication. It is already, known. And so the installation phase, it includes eruption, frenzy, turning point, synergy, and maturity. So here you can see for the industrial revolution the years for that, and they put the steam, railway, steel, electricity, and heavy engineering, and oil, automobile, and mass production, and then information and telecommunication. We had this true for till 2017, but we can even try to. I made this. Try to have an average of this duration for the different kind of surges. But of course, this is, I mean, nothing. It does not. I mean, has nothing to do with science. It's just a possible estimation. So what happens in the different phases? So if you look at here, we have eruption. We have at the beginning of the new technology. Then you have frenzy because we have financial generally bubble time. A lot of people are putting money to develop that technology, for example. And then we have a turning point. We have synergy. So in this case, is production and the use and deployment of this technology. And then you have a maturity. And maturity, you still have you start having a saturation of the diffusion of the technological revolution, and you will start seeing new great surge here. And so where we can, I mean, I just put some numbers where we can be now in 5G. Probably we are here more or less. So we have some use and some implementation, and this is a synergy phase. So we will probably see, even in this case, maturity, and then we will see another great surge coming in some years. Okay, so let me check our main focus to give you some more details. So these are, I mean, the link bandwidth with respect to the link distance, and in this plot, and of course time here, in this plot, you can see on the left bottom side the copper, then you have board, the plane, and then you have on the right side the optical technology into data center network. And if you see, of course, if you have very short distances, you can even have high transmission, high bandwidth, but once you exceed terabits, then you have to go for optical. And if you increase the distance, then you have to swap to the optical technology before. And so this, of course, comes even in the evolution of the time. And what we are generally focusing we call short reach and the long distance. These two are, we are mainly focused there. So let me add some few additional information. So for short reach, what is the main, I mean, characteristic and requirement? So short distance means that they don't need for amplification. At least in principle, if you stay below 80 kilometers, you don't need for EDFA. These are standard erbium doped fiber amplifiers. And the requirement is to have low cost, because generally you go to directly to the final user, low power consumption, and simple configuration. So in general, we prefer to have IMDD still now, even now, but we are thinking now to use even coherent system or a simplified coherent system for short reach because of the, robustness with respect even to chromatic dispersion and to the increase to the rate, because we can increase baud rate and complexity without, increasing the, we can increase the capacity without increasing too much the baud rate. The limiting factor of chromatic dispersion, in this case, and the bandwidth for electro-optical and optical-electronic conversion, and techniques that are consolidated are on-off-keying, PAM4. Now someone is thinking is using PAM8, but PAM8 is reaching some limitation due to the fact that we have 8 different levels, and for these levels they are strongly affected by noise, especially if you go for higher baud rates where you have the electronics that are not good enough, the limitation of the bandwidth, and then you add noise coming from electrical amplifiers and the system. So there is still, work to do there. PAM4 is commercial solution at the moment, and even DMT. I have just some example of what can be done if you are targeting 100 gig, for example, on short reach on uncompensated links. So supposed to have 15 kilometers single mode fiber. We have on-off-keying and PAM4, they suffer severe limitation due to the chromatic dispersion. So we were studying a different approach. It was called CAPS CAPS coding. That CAPS stands for combined amplitude, phase, and shift to reduce GFD sensitivity and increasing the reach. So the idea is here that you want to shape your pulses in order to still have direct detection at the receiver side, but you don't, I mean, you have more robust with respect to the ZVD limitation, so to the chromatic dispersion. And together with, in collaboration with our information theorists here in Pisa, we develop a system. Here's, I mean, some more details of the system. In just to give you an idea, the single pulse that you need to have, it is the blue one in principle, in the in phase, but you even add some qualitative component, but you don't receive the through a coherent system. You will not have in phase and qualitative component after the receiver, but the presence of this qualitative component, it is beneficial for the whole system. So you need to have IQ modulation at the transmitter, but you have still direct detection at the receiver. And this is very powerful, and you can have some simplified hardware implementation if you make some calculation. And at the end, if you look at the system here, it's slightly small, but you can see a Mach-Zehnder, a standard Mach-Zehnder modulator for I, and another Mach-Zehnder modulator for Q, and then you still have, you just have some analog systems here. You have an XOR gate here, it is digital, then you go in the analog and you still have, you have a delay and low pass filtering, and then multiplication. It is very straightforward, and here is an example of the real and imaginary part that you can have as an input signal. But remember, you don't have a direct detection, you have a direct detection at the receiver side, and so by doing this, you can reach this light blue curve where you have the CAPS tree. This is the optical penalty taken at the bit rate at 10 to the minus 3 for a fiber length that can go from 0 to 20 kilometers. So this is for 100 gig. And you see the on-off king here. Then you have the BPSK here, the QPSK, PAM4, CAPS1, that is the dual binary. And then you have PAM8. You see the penalty start from PAM8 very high because you have a lot of levels, 8 levels, and so the noise, as I mentioned before, it is the impact is very strong. And then you have a 3 binary, the red one, and our new conceived system that was CAPS3. And you see that it can extend the reach just by using this pulse shaping approach. And we made even some experiments at 25 G. This was limited by the availability of the hardware, of course. So the source was an external initial laser, then an accumulator, and a single photodiode direct detection receiver. You can see here the comparison between the blue, the straight line and the dots, or square or a circle, that are the experimental one. So on-off keying, PAM4 and CAPS3, you see the good agreement, and you can see how the CAPS3 performs with respect to the PAM4 with the same capacity of 100. This was for 50 gig per second, but you can see here the PAM4 back to back and CAPS3 back to back, and after 50 kilometers is gone, and CAPS3 is still working, and is still working at 80 kilometers. So it was published, and it was really a strong achievement here. When you apply the message is you can apply some theory in order to give the good shape and to try to limit the impact of GVD. I will give just another information about another technique that is mainly for transport for longer reach. that is called time frequency packing. I will spend some few minutes about that because that was the technique that we did use for in the field trial, as was mentioned at the beginning in the introduction. And so it is very strong because we developed this technique, and now a lot of strong companies like Huawei or Nokia, Siemens, they are considering this technique that we developed. But the thing that is important even in training is the concept that is very strong. So generally, in most of communications, what we talk about it is, a transmission that deals with orthogonal signals. It means that if we talk about WDM, you have different wavelengths and they are separated. So you just can extract through a filter your wavelength and it's there. So you don't have overlap. If you have overlap, it is crosstalk and it is noise. And this is orthogonal. You don't have inter-carrier interference. And you can have OFDM or CDMA, but all there are orthogonal. If you have a representation of your signal in the time and frequency, here you see this circle represents your signal that has an extension in frequency, a bandwidth, an extension in time, it is a time duration, but you can always select ideally one symbol with respect to the other and identify it without overlap, or a frequency with respect to the other without overlap. This is it is not the only way of transmitting. You can have some different transmission when you have non-orthogonal. You can have overlap either in frequency or in time. And so single, multiple carriers may overlap in frequency, but even in time. And this is called faster than Nyquist signaling. In the faster than Nyquist signaling, you have overlap in frequency and time. Here you have a design criterion that is no reduction of the minimum Euclidean distance with respect to the Nyquist case. And the theory says that you can recover for the information if you know the amount of inter-symbol interference or inter-carrier interference that you are adding. Then you can design your receiver in order to recover for that. There is a slightly different approach that is called time frequency packing. The principle is the same, but what we want to do in the term of the design criterion is to maximize the spectral efficiency, but with the design constraint receiver complexity. So you want to give the constraints to your receiver in terms of complexity. Once you have your receiver there and it is feasible, then you want to know the maximum spectral efficiency you can get. Spectral efficiency means you can pack more in the time and in the frequency your signal, and that gives you an increase in the spectral efficiency. This comes more evident if you look at the information theory that stays below this. So if you have a channel with memory with input X data and Y data, the information rate is a function, I is a function of X and Y, and the spectral efficiency is defined as the information rate divided by the F and T, where F is the frequency spacing and T is the symbol time. So if you plot the spectral efficiency with respect to these two, information rate and F and T, with respect to F and T, so you see that the information rate is, in principle, it always grows. But you have the spectral efficiency that has this behavior with respect to FT. So at the end, you can have, if you look at the spectral efficiency globally, then you can have a maximum in terms of spectral efficiency with respect to the product F and T. And so we want to work here because in this case we are maximizing the spectral efficiency. So we can. This means that we can pack and we can accept some interchannel interference or intersymbol interference. Means that interference increases, but the information rate, but the spectral efficiency can improve even if the information rate will decrease. We are introducing a no inter-symbol intercarrier interference, and we use a low complexity receiver and a proper code ensuring error-free transmission. And this, the theory says that can be found, and it is possible to find and use these codes. And here is an example of spectral efficiency, theoretical computed with respect to the channel limit, that is the black curve. And for different, here is QPSK with the orthogonal signaling. It means that you don't use frequency, entire frequency packing. Then you have 8 PSK and 16 QM, and you can see that all these have a QPSK with time frequency, with time packing, with this different kind of filters, with cosine filters and Gaussian filter, but you can have a better performance with respect to the orthogonal signal. You can have a very high spectral efficiency using that. And actually, this is what we did. Let me go fast to some results that I want to show you. Let me skip this. Sorry. Yes. So for long reach, means link distance larger than 80 kilometers, you want to have large spectral efficiency. Even you want to have low DSP complexity, low power consumption, and larger wavelength stability. And the limiting factor are DSP, visibility, nonlinear effect, and the consolidated choice is Nyquist 16 QM, but even nowadays 64 QM. So these are the spectral efficiency as a function of the optical reach for some commercial systems here, and even from research here. And you can see the different companies. They even probably changed the names here after acquisition, I think. But yes, we have some reference point. Using our time frequency packing, we could have these circles. And this means that by changing our code rate, it is possible even to have higher granularity. And this gives much more flexibility. So the system is the same, the speed is the same, the rate is the same, but you change just the coding and the coding rates. And this was actually used even in the field trial. We made the first comparison between Nyquist and time frequency packing together with the Coriant within a European project. I can just show you here. It is the Nyquist WDM super channel, 5 channels, and here is the time frequency packing super channel that is within the standard traffic here, and here in red is the standard WSS filter shapes, and we made a comparison, and here you can see how the system, the Nyquist WDM system behaves with respect to the distance. So you see that after 1,600 kilometers, it is not possible to have error-free operation because it is below the threshold of the FEC, and this one, the start one, it is the Nyquist, the time frequency packing, and where n is the number of iteration because we have two decoding. We still have a low number of iteration. Here it's 10, and we still have a 10 to the minus 6 operation for up to more, at least, almost 2,000 kilometers. And this is even a comparison with respect to the filter bandwidth, and we can see that time frequency packing, it's much more robust with respect even to the filtering. Last information, we made this two information. We made this in a field trial. I will not go through detail because I don't want to. The time is limited. But we packed this and we went to Sydney, and we installed the system in the link between Sydney and Melbourne. And we made measure in a single way, even in the loop back, and here are some results, some pictures. The point is that using our time frequency packing, even by including a filter in the line, so in Canberra was WSS, we could reach at that time the record in terms of spectral efficiency times distance product, and we reached like 9,293 bit per second per hertz per kilometers. And this was, I mean, the measure was performed on the central channel. As I was mentioning, it is possible to, I mean, change the code rate without changing any kind of transceiver characteristic, even in terms of baud rate. So you see, if you have a code rate of 9 or 10 or 8 or 9, 5 or 6, 3 or 4, what does it mean? That you add a redundancy that is increasing in this direction, of course. So you are wasting 1 bit over 10, 2 bits over 9, sorry, 1 bit over 9, 1 bit over 6, or 1 bit over 4, but you can reach much more distance. You can deal with a lower OSNR. And so this gives you the possibility to make adaptation of transmission parameter in an elastic optical network. So we made this kind of adaptation, and we made even self-adaptation procedure for the optimization. So just to give you an idea, and we go fast here, this was very interesting because we had in this case 1, 2, 3, 4, 5, 6, 7, 8 channels in a 200 gigahertz of bandwidth. And by we try to pack more, to put the lasers more close to each other. And by doing that, by just checking the quality of the transmission, so by checking the bit rate at the end, we were able to squeeze the multi-channel, the comb, and then to save one slot. And at the end, after closing the WSS, it was possible to save one full slot of transmission, the slot of 12.5 gigahertz. So this can give you an idea of what can be done using optimization. This is very flexible and can be used in a network. Actually, we did even some activity even in a field trial with self-adaptation here in Italy. I think I have a picture. Yes, this. Oh, sorry. Oh, sorry. This is the picture of the system that was used for field trial and adaptation in the field using even the network control. Finally, here's what will be the next. It is interesting to figure out what will be next, if it will be human ubiquity, teletransportation, and multitasking. I use this generally to close this picture. It was even funny to me and to the audience generally, but yeah, just to try to figure out what will be the future of communication and the technologies that will be needed. So I thank you. I think that the time is over, and sorry if I even use a little bit more of your break. I think if you have questions here, I have more material. If you are more curious about time frequency packing and either other possible technical technological solution that we adopted or we are using in our research activities. Thank you very much. Any question?
Hello.
Yeah.
Dr. Aslan, can you please moderate the questions one by one? People have questions we can ask, and so that Professor Luca can respond.
Prof. Right.
Yes, there is a question here. Yeah, Arslan, can you please?
Yeah, we have lost. We did lose the voice for some time, but now I think you are back. So I don't know what happened in the past 1 minute, and we all don't know. There was some problem with the audio. So yes, there are questions in the chat. So if Professor Luca is taking those questions, I'm not sure.
Yes, he's waiting for the questions.
Yes, I'm here.
These are not related to the talk.
Which one? I mean, in the chat.
I think
Yeah.
it's
I have. I think there are some
related to
asking for.
Dr. Imran, can you
Yes.
take control
Luca,
until I
the
get
question,
the
there is a question
audio
about.
back here? I think if you can hear me, because we cannot hear you.
Yeah.
Again,
So let me ask the question. You know, I don't know
can
if
you
it
take
is.
control of the QA session? Just look at the chat message, and there are some questions for Professor Luca.
Sure. Luca, there is a question. It says, in theory, the fiber is 10 gigabit per second, but when testing from server to server, the bandwidth cannot reach SFP plus. So how can from the optical team can confirm that it is not from the fiber? I don't know if I understood the question.
I didn't.
Yeah.
Let me find when testing from server to server, the bandwidth cannot reach. How can from optical team can confirm that is not from fiber? No, I cannot understand the question. Can you rephrase, please? Because it is not clear to me.
Yeah. Vuta, I think it's a question from you. Can you please even orally ask that, you know?
In the meanwhile, I was reading about the holographic communication before. I'm not an expert in holographic communication, but I have to say that looking at the question, it is how to handle data loss in holographic communication. Actually, you cannot handle data loss even in some application for standard telecommunication. But time. Oh, sorry, it is TCP, or I don't know. Is it for me, or because TCP is not? I thought it was time frequency packing. If it is related to time frequency packing, to TFP, we are not. I mean, we are not dealing with data loss. We can add the idea is that we are artificially adding some inter-symbol interference or intercarrier interference, but we know that they are adding, and there is a theory says that you can always find code that can recover for that. So at the end, you have your information. So you can recover for that. Of course, you have to pay in terms of DSP. And the complexity of your receiver and your coding and decoding technique, it depends on the amount of inter-symbol interference or intercarrier interference that you are adding.
Okay. Luca, I tried to read in the question of from Vuta again.
Yes.
What I understood is that, you know, he's telling that, for example, there is a 10 gigabit per second link.
Yes.
They're using pluggable SFPs.
Yes.
So he is saying that if we cannot reach the desired bandwidth data rate level, is it a problem of the fiber?
So they say that if they don't reach but I mean, you cannot. I mean, I don't know if you have. I don't know if I got the question, but
okay, let me. I think what I understood is that from his question that if there is a link, 10 gigabit per second link, and we are not achieving the exact data rate, is it the problem of the fiber or of the transceivers?
It depends. It depends on. If the fiber stays within the specification of the transceivers, then it is a problem of. Probably the transceivers is not working in the right operation mode. If the fiber is, for example, longer, or you have more attenuation than expected, for example, in a point where you are plugging some connectors or something like that, then you can have low power, and your transceiver it is not working within the specification. So if I got the question, you have to check if the link it is suitable for that SFP specification.
Okay. And there is another question which says, which type of optical fiber used for the nitrous WDM?
Okay.
G.654.
Okay, so generally speaking, the nitrous WDM technology did replace standard WDM system. So they are trying to install, with all different kind of fibers. So the G652, 3, and even 4. Of course, in the dispersion shifted one, there is a higher problem with respect to nonlinearities that we know very well. And so we know that who made this deployment and installation of that fiber, did not consider the nonlinear effect, and so they cannot use too much power for that. But if you have short links, then they want to exploit the maximum of the capacity of the bandwidth, so they are packing and they use nitrous WDM. So I have to say that right now, when you have, it is almost standard, so you can use nitrous WDM technology more or less everywhere in the fiber. Of course, you have to deal with the nonlinearities in this dispersion shifted fiber.
Sure. Okay. There is a follow-up question from the same from Luca, which was about the 10 gigabit link problem. So, okay, I think he wants to resolve the conflict between the people who are working in data center and the people who are managing the fiber. So his question is, so how can from the fiber team can have the proof to show that the fiber is okay?
I think that if you measure the power,
exactly,
that you have when you at the receiver side, if the power is the one that is expected from the design of the power budget, something, or it is within the specification of the transceiver as a received power, then in that case the fiber is okay, in my opinion. If you have just fiber, if you even have some other device into the fiber, like a WSS, some filters or something like that, you need even to check if you want the optical spectrum. So you have to measure the optical spectrum and see if you have any kind of distortion. But the power is the first thing. If you have the power, you should have the fiber should be okay.
Okay, yeah. Let me add into this from the operational point of view, because I have a little experience in the network side. So what you can do with is that whenever your link is commissioned, try to get the optical parameters, as Professor Luca said. The losses of the link, and keep it with you. Whenever those losses will increase, then you will know that this is a problem of the fiber. Is there any other question?
Okay, any question from the audience sitting right here? Anyone? Okay, so we have got our problem rectified. It was battery. The battery died out actually. Anyway, so if there are no further questions, we can wrap it up, I think, right? Because again, we are behind schedule. So we are stopping people from getting lunch. So I would like to thank Professor Luca. Thank you so very much for your time. It was great to have you have your talk, have you with us in this SDON training event. And also I would like to thank on behalf of NUST your support throughout the entire project, throughout this project that me and Dr. Imran carried out with our respective teams together. So thank you very much. Thank you very much for joining.
Thank you.
Thanks a lot.
Sorry for being a little bit long in the presentation. Thank you.
No, it's all okay. All okay. Thank you so much. Thank you.
Thank you.
Okay, so to everyone sitting here and in the virtual audience, we will reconvene again. So we are a bit behind schedule. So let's make the reconvening time also. So we'll reconvene at around 2:20 Pakistan Standard Time. Okay, so 2:20 we'll reconvene, and then there is a slight change as I communicated at the start of the day. So initially, Dr. Imran will have his talk on the NREN perspective and operator techno-economic analysis and related stuff about obviously in the context of open optical networks. And then his talk actually has to be divided into two parts because of the availability of Jan Kundrat from CESNET. So he will be giving a talk from 3 to 4 Pakistan Standard Time. So after the break at 2:20, we will start with Dr. Imran and then move to Jan Kundrat, and then Dr. Imran will finish the second half of his talk on operator's perspective. Okay, so thanks a lot for joining in the morning session, and I'll see all of you after about 40-45 minutes. Okay, so see you. Let's reconvene at 2:20. Thank you.